All right, thank you very much. Thank you for inviting me, Tangle. I'm very happy to be here. These 4 lectures, we thought we would do a survey of induced subgraph theory and do some recent theorems, but also cover an introduction. I'm trying to arrange these lectures so that you don't need to know very much, but probably you need to know a little bit. And does anybody not know any graph theory? Everybody knows some graph theory, right? Is anybody doesn't know any graph theory? No? Good. Excellent. Okay. I mean, you don't need very much, but you need a little bit maybe. So this talk is going to be just a survey of everything, and then the other 3 talks are going to be focusing on each on one area. But today I'm going to try and cover everything very quickly. So, induced subgraphs. So you know what a subgraph of a graph is? You just go to, for an induced subgraph, you take some of the vertices and you take all of the edges contained inside of there. So, for instance, if I take, let's say that graph, and I take, I don't know, what would be a good example? That. And this is a subgraph of that because you can see, I mean, the vertices 1, 2, 3, 4, 5. But it's not an induced subgraph because this edge is missing. If I want to use the vertices 3 and the vertices 5, then I have to use the edge between them. You can't delete edges. So again, another definition is, you go to a subgraph by deleting vertices. You go to a subgraph just by deleting vertices. You can't delete edges. You all know this, right? Does everybody know this already? Was that news to anybody? Okay, good. I don't really know how much you know. So if I tell you stuff you already know, I'm sorry. But so induced subgraph. Let me give you another definition while I'm here. An ideal of graphs means a set of graphs, let's say F of graphs, such that if some graph is in F and H is isomorphic to an induced subgraph, then H is in F. So it's just a class of graphs closed under taking induced subgraphs. So where do you get ideals? You can get ideals in 3 different ways. You can describe ideals in 3 ways. Well, at least 3 ways. You could take the ideals of all graphs. You could characterize ideals by the graphs they don't contain. You could exclude some graphs. You could say the ideal of graphs not containing any of the following graphs. And then make a list. So if I give you a list of graphs here, you can take the ideal of all graphs that don't contain them, and that's an ideal. That's describing an ideal by forbidden induced subgraphs. So you might take, for instance, the graphs with no odd hole. What's a hole in a graph? It means a cycle, a cycle which is an induced subgraph of length at least 4. And an odd hole just means a hole of odd length. So that would be, that's an ideal. The class of all graphs with no odd hole is an ideal, but but it's defined by excluding something. Another way you could define an ideal is by properties. You could say the ideal of all graphs such that the chromatic number equals the clique number. Let me say of all graphs G such that that equals that for all induced subgraphs. And that's a definition of an ideal by properties. We're asking, we just want to look at all the graphs that have a certain property. Or you could define ideals by constructions. So this is exclusion. This is property. And then there's construction. For instance, the ideal of all line graphs. Or, I don't know, the ideal of all bipartite graphs, the ideal of all, graphs with some construction. But there are three different ways to define ideals. And you get nice theorems that when two of them are equivalent, the ideal of all graphs with this property is the same as the ideal of all graphs, you can construct that way. I mean, there are pretty theorems like that, and that's what I want to talk about. That's what these series of talks is about. Anyway, let's start at the bottom. Let's think about, fix a graph H, and let's look at the ideal of all graphs not containing H. H-free graphs. H-free means no induced subgraph isomorphic to H. So that's a character. That's an ideal defined by exclusion. And it would be nice, if I want to look at all graphs that don't contain this graph. How do you construct them all? Or what properties do they have? Let's see, what can we do? So, if H is just, say, that graph, two vertices, no edges, then you can do it. What's the answer?
Complete graphs.
Complete graphs, yes. So let's say I of H. I of H is the set of all complete graphs. And similarly, if H is this graph, it's the graphs with no edges. That's trivial. And notice that one nice thing about doing induced subgraphs is if you know the answer for one graph, you also know the answer for the complement. Because you just take whatever graphs here, you put the complements here, and that's the answer for the complement. Let's do another one. What about, say, two-edged paths? What are the graphs that don't contain that as an induced subgraph? Which means this is not an edge, right? Which graphs don't contain that as an induced subgraph? Can you tell me?
Triangle-free.
What?
Triangle-free.
No, triangle. For instance, a triangle would be legal. It doesn't contain that. Triangle doesn't contain that, so that's not.
Disjoint union of complete graphs.
Disjoint union of complete graphs. So all graphs that are disjoint unions of complete graphs. Because what this says is that being adjacent is an equivalence relation. If A is adjacent to B and B is adjacent to C, then A must be adjacent to C. which means you break the vertices into equivalence classes. And therefore, by complements, we can also do this. And you take, instead of the disjoint unions of complete graphs, you take the complement, which is a complete multipartite graph. So you can break the graph into many sets, many stable sets, which are pairwise complete to one another. Well, so that's, all right, we can do these little graphs. What happens if we get a bit bigger? Let's look at some 4-vertex graphs. Well, graphs don't contain that. That's getting a little bit more interesting. There's a nice theorem there. And I mean, if you don't know the answer, if you know the answer, that's fine. If you don't know the answer, you probably can't guess. So the answer is, so here's how you can build the graphs that don't contain this. You can take two graphs you already built and take their disjoint union, or you can take two graphs you already built, take their disjoint union, and make this complete to that. So, for instance, here's a graph I've already made. Here's another graph I've already made. I take their disjoint union and make all these vertices join to all of those. So, two constructions. You can either take disjoint unions of two graphs, or take the disjoint union in the complement, which is what this is, right? So, for instance, I start with 1-vertex graphs, I take another 1-vertex graph, I put an edge between. So now I can build this, and I can build that, and I put edges between, and I take this and that, and I put edges between them all. This construction. So these things are called cographs. The graphs you can build by taking disjoint unions and taking disjoint unions in the complement. And they're exactly the graphs that don't contain this thing, which is P4. And see what we're getting. We're getting back to this way of describing ideals. The ideals are defined by excluding something, but we're getting constructions for the answers. We're getting a construction for the graphs that don't contain this. I wish I knew exactly what a construction was. I spend my life proving construction theorems, structure theorems. I don't have a good definition of what is a structure theorem. I mean, we did 3-vertex graphs here, and now I'm doing 4-vertex graphs. We missed a 3-vertex graph. There's a 3-vertex graph we didn't do. What about a triangle? Which graphs don't contain a triangle as an induced subgraph? They're just the triangle-free graphs. Is that a construction? I mean, is that a construction? I don't know. Does that count? Is there a deep theorem that we just don't know about how to construct all triangle-free graphs? Or is that the answer already? You just build graphs and you add edges as long as you don't make a triangle. And is that a construction? I don't know. But I mean, all I can say is it's triangle-free, which is sort of trivial. That's annoying. I mean, it would be nice to have that for any graph, you get a decent way to construct the graphs that don't contain it. I don't think this is a decent way to construct anything. I don't like triangle-free graphs, but I don't know how to do better. Anyway, so that's a gap. But what can we do for 4-vertex paths? For 4-vertex graphs? We can do this one. Let's do some others. Can you do this one? I mean, you can do the complement of that, but it doesn't give you anything new because it's the same. What about that? That one I want to do in detail because it's nice. Let me show you. This I think is called is this a paw? Does anybody know? I'm going to call it a paw. So that may be the wrong name, but for today we'll call it a paw. What are the graphs with no paw as an induced subgraph? So can you give me some examples? What are graphs with no paw? Give me an example of a graph with no paw. Cycles, okay. Bigger graphs.
Triangle free.
Triangle free, okay, triangle free. That's one example. Can you give me a graph which has a triangle and doesn't have a pole? Yeah, triangle. Can you give me another one? What? Complete graphs. How about even more? What? Well, there's complete multipartite. Which generalizes that. So I don't need to list these anymore because it's a special case of that. And that's the answer. That, well, not quite. If you're, here's the theorem that if you don't contain a pore if and only if each component is either triangle free or complete multipartite. And let's see a proof. So if there's no triangle, then fine. So we can assume the graph's connected. So we not go so fast. It's an if and only if statement. One half is easy. The if half is easy. If these graphs don't contain pores, we have to prove the reverse. If I got a graph with no pore, I need to prove it satisfies that. Well, I might as well assume the graph's connected, because if each component satisfies this, then the whole graph satisfies this. So we can assume G has no pore and G is connected. And we can assume G has a triangle. So let's look at the biggest clique that it contains. Take the biggest clique. Clique is a complete graph, complete subgraph, a set of vertices all adjacent to one another. In this talk, by the way, I never have parallel edges. If you're doing minors, you care about parallel edges, but for induced subgraphs, we don't care. So no parallel edges and no loops. The clique just means a set of vertices that makes an induced subgraph, which is a complete graph. So here I've got, here's the biggest clique in G. They're all joined to one another. Now, look at it. Are there any more vertices? Well, might be. Maybe we can blow, and there might be a vertex like this. It can't be joined to all of them because that would be a bigger clique. But there might be vertices joined to all except one, and that's possible. There's still no claw. So it would blow up to be a complete multipartite graph. Let's blow it up to be a complete multipartite graph. Take the biggest complete multipartite graph where the number of levels equals the maximum clique. Omega means the clique number, the size of the largest clique. So start with the largest clique and then grow it to be a complete multipartite graph until you can't grow it anymore. No, maybe there's more. If there are no more vertices, we're done. The whole graph is complete multipartite. So I can assume there's more vertices. And since the graph's connected, there's a vertex with a neighbor here somewhere. Now, what is it joined to? If it's got a neighbor here and a neighbor there and a non-neighbor there, that's not not a pole. Let me try again. If it's got a neighbor and non-neighbors in two of them, that's a pole. That's impossible. You have, these make a triangle, and these join to one vertex of the triangle. So as soon as you have one neighbor, there can't be two of the sets where you have non-neighbors. So as soon as you have one neighbor, you're completely joined to all except one of the sets. And what goes on in the last set? Can you have any neighbors there? Can you have any neighbors there? No, you can't, because that would be a bigger clique. We already started with the biggest clique. You just take one vertex from each, and that vertex, and that vertex, and that's a bigger clique than the clique we started with. So that can't happen. So you can't have any neighbors in the last set. Then this vertex can be added to the last set, and it's a bigger, complete multivariate graph. That's impossible. So there, that's the only proof I'm going to do today. But isn't that? I mean, that shows you something. It shows that for here we were looking for excluding an induced subgraph, and we got two answers. We got complete multivariate graphs, and we got triangle-free graphs. They're different, and the general answer is you combine them, and that happens a lot. That you exclude an induced subgraph, and the answer is you can build there's this construction, and there's that construction, and there's the other construction, and there's things you can make by putting them together generally in more complicated ways than just disjoint union, but here it's just disjoint union. Sometimes you need more complicated operations, but the same thing happens a lot. Anyway, what was I was doing my list of little graphs. We did the 4H path, we did the pole. What else can we do? So we can do the complements. The complement of a pole is something. What's the complement of a pole? It's this. What about H is that? Can we do that? What's I of H? That one looks complicated, but actually it's got a nice answer. Here's what you can do. Take a bipartite graph, not complete bipartite, just a bipartite graph with no cycle of length less at most 6. I mean, if we take graphs with no triangle, then I guess I can take bipartite graphs with no cycle of length at most 6. That's if one is a construction, the other is a construction, right? So take graphs with no cycle of... Now make another graph where these are the vertices, and for every vertex here, so it's joined to some of these, what you do is you remove that vertex and make its neighbors a clique. So for every vertex on the left, you remove it and make its neighbors a clique. And this graph does not contain that, and every graph not containing that you can build by this process. So that's a decent answer. It's not very pretty, but it's all right. I think that counts as a solution. What other graphs are there on 4 vertices? Well, there's C4. And what's I of H? Don't know. You wouldn't think that was so difficult. It's just the graphs with no induced cycle of length 4. And the problem is it's not that we don't know the answer. It seems possible that there isn't an answer. It's the same as triangle-free graphs. There's nothing to say. Maybe there's just nothing to say. And there's really no way to is there no construction? But anyway, there's no good theorem here. There's nothing known. I don't know whether it exists or not, but it's certainly not proved. And I don't know what the answer should be. And of course, one thing we haven't really looked at all is K4. And, well, K4 is the same as K3. You just throw in edges and don't make a K4. I mean, that's the best you can say. And then I think, no, I listed them all, I think. Oh no, I forgot an important one. I forgot the claw. So which graphs don't contain a claw? That turns out to be a really nice question. So that's a question where there is an answer, but it was very difficult. But it's a theorem, and Maria and I proved it. That's the first hard theorem I wanted to mention. So examples are for line graphs. If you take a line graph of any graph, it doesn't contain a claw. You can take, there's something called circular interval graphs. What's that? Well, you put vertices in a circle, and you choose intervals, and you turn the intervals into cliques. Not so bad. Like this. So each interval becomes a clique. Wait, and I'm lost now. I think, whatever, you can't understand the picture anyway, but you choose intervals from the circle, and you make each interval be a clique. And that's claw-free. And it's not a line graph, it's different. And the third class is, say, the icosahedron. You know, 20 vertices, you know the icosahedron graph. That's claw-free. And the fourth is the Schläfli graph. That's a nice graph, very symmetrical, on 27 vertices. 27, maybe I won't give you the exact definition, but it's made up of 3 disjoint copies of the line graph of K33 with edges between them appropriately. And this is claw-free, and there are various other constructions of claw-free graphs. But we proved a theorem that every claw-free graph can be built from these by gluing them together. It's like this theorem that, you know, every pole-free graph is either complete multipartite or triangle-free, or made from them by gluing them together. It's the same here, except the gluing operation is different. It's not just disjoint union, it's more complicated, but it's the same in principle. So theorem is G is claw-free if and only if G can be constructed from these classes by operations, which I won't. So I'm not listing the classes and I'm not listing the operations, so it's not very clear. But it's a big list of classes and a big list of operations, but there is a theorem. I mean, the point just is that there is a theorem and it's complicated. So another answer, I mean, so what is a construction? What is a construction? I mean, if I want to know, does a graph contain a claw? If I want an algorithm, that's easy, right? You just check all subsets of size 4. It takes you time n to the 4th. So I mean, is that a construction? I don't think that's a construction. That's an algorithm, it's not a construction. But this is a construction. I wish I could make the difference clear. But I hope at least you get the spirit of what is a construction. All right, so that's the story for 4-vertex graph. The story doesn't go much further. What about 5-vertex graphs? I mean, there are all kinds of interesting 5-vertex graphs. You know, there's a C5. I would like to know the answer for that. There's a 4-edge path. I mean, it's not known. This is not known. There is one that's known, and it's the bull. And then I of h is known. And this is the theorem of Maria. I won't tell you the theorem. It's another one of these big horrible theorems. It's like the claw-free theorem. I mean, it's a great, I mean, it takes you, I mean, the statement of it is long, right? It's not, maybe not quite as long as the statement of the claw-free theorem, but it's still pretty nasty. Let me not do it. But it exists. Just the one exists. Just one 5-vertex graph. And no 6-vertex graphs. That's the end of the story. We don't know any more theorems. Any more exact structure theorems that are equivalent to excluding the subgraph. That's the end of the list. All right, well there. What can we do now? That was
Does the list involve triangle-free graphs?
yeah, the list involves triangle. Also here, I forgot to say, there's triangle-free graphs. No, not triangle-free graphs. Complements of triangle-free graphs. Because complement of the claw has a triangle, so if your graph doesn't have any triangles in its complement, it must be claw-free. Well, so what can we do now? What?
Consider two graphs.
Yeah, maybe. I mean, you can also do it the other way around. So if you fix a graph and you get an answer structure, 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 or combinations of them. Seems to happen. Or what you could do is you start with a structure and you ask, you know, take an ideal defined that way, and I would like to find the graphs I have to exclude. So the minimal graphs that don't have the structure. Like, if I wanted to know the minimal graphs that are not line graphs, I would like to say a graph is a line graph if and only if it doesn't contain any of these graphs. But then you're not just excluding one graph, you're excluding a lot. But there are many theorems like that. Let me not do them because they exist and there is a lot of them, and I'm not so much interested in the series of talks. But it's true. If I start with a structure and look for the excluded subgraphs, there are theorems of that kind. But let me not do them. Excuse me. I mean, if we're doing minors, I don't know how much you know about minors of graphs. So a little graph is a minor of a big graph if you can get it by going to a subgraph and then contracting edges. I don't want to say much about minors, but I used to work a lot on minors, and nowadays I work on induced subgraphs more. And minors is much, the theory of minors is much more developed than the theory of induced subgraphs. It's much more satisfactory than the theory of induced subgraphs. What's the difference? I mean, it's the same with minors. If I want to know which graphs don't have a K4 minor, I can do it. Which graphs don't have, I don't know, a K5 minor, I can do it. Which graphs don't have a K33 minor, you can do it. But if I say which graphs don't have a K10 minor, you can't do it. It's too hard. So again, you can give exact answers for little graphs. But when the graphs get big enough, you can't do it anymore, as you expect. The difference between induced subgraphs and minors is, well, one important difference is the following, that the theorem, so there is a list of constructed ideals So I mean ideals with this kind of description. The set of all graphs you can build by doing some operations. There is a list of constructive ideals So they look like this. So say F1, F2, and they're getting bigger. F3, each includes the next. And none of them is equal to they're not equal to the set of all graphs. So they're all of them proper ideals. Such that every proper ideal is a subset of one of them. So now by an ideal I mean an ideal of minors, a set of graphs closed undertaking minors. And if you have a, I'm sorry, I'm now talking about minors just for a minute. So we have a set of constructed ideals such that for every minor ideal not equal to the set of all graphs is a subset of one of them. That we know for minors. We don't know that theorem for induced subgraphs. We don't have a construction, we don't have a sequence of constructed ideals so that eventually you swallow every ideal for induced subgraphs, and that's different. This is the graph minus structure theorem. That's a very hard theorem, a theorem of Neil Robertson and me, and it took us, it was 20 papers, and we didn't really use them all, but several papers anyway were used to prove this. Maybe we needed 10 papers to prove this theorem, and they're big long papers. That's a lot of work. And they said this theorem for minors had all kinds of nice consequences. And if you could do it for induced subgraphs, it would also have nice consequences for induced subgraphs, but it's just not done. I think that's the biggest, most important question for induced subgraphs. I think that's the most important question for induced subgraphs. Can you get a sequence of constructed ideals like this so that every ideal is contained in one of them? But it's completely open. We don't have a clue. There's no conjecture. There's nothing. Anyway, so that's one important difference between minors and induced subgraphs. But now back to induced subgraphs. Well, so if I take the set of all graphs, that's an ideal. Or if I take any other ideal, it's also an ideal. They're different. I mean, you'd think if you look at minors, you take the ideal of all graphs and the ideal of all graphs, any proper ideal, they're really different. They're really different in the sense that, for instance, you have all the graphs in a proper ideal have bounded average degree. Their average degree is only a constant. The number of edges is only constant times the number of vertices in any ideal, except the ideal of all graphs. If you take the ideal of all graphs, it's false. But is there some quantitative difference qualitative difference, between the proper induced subgraph ideals and the ideal of all graphs? We don't know. Well, kind of we do. If we give up on constructions, we can't do constructions. We don't know how to do it. Let's ask for something easier. There was an approach of Erdős and Heinel, that look at the Ramsey number. So Ramsey's theorem says if you have a big enough graph, then you either contain a large clique or a large independent set. But how big does it have to be? If I have an n-vertex graph, how big a clique or stable set can I guarantee? Log n. Constant log n, I think. Yeah, more or less log n. If in any n-vertex graph there is a clique or a stable set. I mean, stable set means independent set. I say stable set because independent is used for too much. Stable set of size at least log n. I'm not telling you the base of logs, so that way I don't have to worry about the constant in front. And this is the truth. You can give examples, n-vertex graphs that have stable sets that big but don't have anything bigger. I mean, you can't give examples, but there exist examples. You do random graphs. So this is best possible. Well, what happens if you exclude a graph? Fix a graph H and look at the graphs that don't contain it. And if G is H free and has n vertices, then G has a clique or stable set of size what? Well, you can do better than log n now. It's a theorem of Erdős and Heinel that you can do e to the constant root log n, where the constant depends on h. So that's bigger. It's bigger than just log n. I mean, you need to think, but it's true. This is an e. Can you read it? So they're different. The Ramsey number is different. I mean, the way you construct these graphs is you take random graphs, you put in edge density, add edges with probability of half, and that's really how you do it. That's the only. I believe that's the only known construction. And if you have a random graph, it'll contain everything as an induced subgraph. So if I look at graphs that, we want to know if I'm looking at graphs that are not random, how close can you get to this without using the random construction? Well, how exactly do you make that precise? But one way to make it precise is if you exclude a graph, so that guarantees you're not using random graphs, then now the clique or stable set is much bigger. And there's a conjecture called the Erdős-Heinel conjecture. So this is a theorem of Erdős and Heinel. So in all the same statement, except you change this to something bigger. So it's at least n to the, well, C of h, but different C of h. Let me say D of h. So for instance, let's do some examples. If you take, let's say h is, I don't know, this graph. So then the graphs not containing h are just complete disjoint unions of cliques. Well, if I have n vertices, and I have a graph which is a disjoint union of cliques, maybe one of the cliques is big. And if not, then I have to have many cliques. Either one of the cliques has size at least root n, or I need root n different cliques. So either I get a clique of size root n, or I get a stable set of size root n, one vertex from each. So for this graph, we can take d of h as a half. If we did h was the 3-edge path, you can figure it out, and d of h once again is a half. If you did I forget what the answer is for a claw. We must have worked it out, but I forget. Is it really a half again?
I think it's a third.
It's a third. Okay. So we think. For the bull, it's a quarter. And you can give examples to show that these are all best possible. Yeah. That's Maria and Safra. But it seems true that for any excluded subgraph, that this is true, and that's this becomes a sort of test. Do you understand the graphs that don't contain H? Fix a graph H. Do I understand the graphs that don't have H as an induced subgraph? Well, if you can prove the Erdős-Heinel conjecture, it means you probably do understand them. If you can't, then probably you definitely don't understand them. And I mean, assuming it's true, of course. So, which graphs? Let's say H has the Erdős-Heinel property if there exists a CH such that every n vertex H free graph has a Cliquot stable set of size n to the C of H. I was calling it D of H before. Should I keep on calling it D of H? So what's known? And we know that I just showed you that these little graphs, the bull, claw, these have the Erdős-Heinel property. And the conjecture is all graphs have the Erdős-Heinel property. But what can we prove? I mean, we can get better than this. There's a theorem of Alain wait, I wrote it down. Alain Park and Solomorchi. That says, suppose I have two graphs that have the Erdős-Heinel property. So for instance, if I take, say, this graph and the bull, if H1 and H2 have the Erdős-Heinel property, and I substitute one of them for a vertex of the other. So for instance, if I substitute the bull for this vertex of the 4H path, 3H path, then I get a put a bull here, and all these vertices are now going to be joined to that one. So is it clear what the construction is? You substitute a graph for a vertex of another graph. And right, so I have a graph, H1, I have a graph H2, and here's a vertex of it, and it has some neighbors. And I'm going to put this H1 instead of that vertex. So I have the rest of H2 here, but now I'll put a copy of H1, and it will be joined to all the people that used to be joined to that vertex. So this is called substitution. Anything you can get by substitution. If H1 and H2, then every graph obtained by substituting H2, H1 and H2 has the Erdős-Heinel property. So that's something. It doesn't get you very far, but at least it does some of the so now we can do all the 4 vertex graphs, because, like the K4, it's got from substituting from K2. And C4 is got from substituting from C4. We don't have a structure theorem for excluding it, but I can get it from this graph by substituting it a 2 vertex graph for the middle. So the 2 graphs we couldn't do on 4 vertices, we couldn't get structure theorem. We can prove have the Erdős-Heinel property because we can make them by substitution. And you can do some graphs on 5 vertices. But still you cannot do, say, C5. Does this have the Erdős-Heinel property? Don't know. It's not made by substitution. Does the 4-edge path have the Edersheimel property? Again, we don't know. I've now told you the complete list. All the graphs that we know that have the Edersheimel property are these basic ones, and what you can make by substitution. Those are the only ones that it's proof for. But it's conjectured to be true for all graphs. So, big gap. Yes?
So the graphs you listed there, the 3-path, 4-path, and bull, that have the Edersheimel property, does the proof use that you know how to construct these ideas?
So,
Is that how you know?
well, these little ones, the theorems are easy, so you might as well use the theorem. For the bull, you don't need the hard theorem. Since we've done so well with induced subgraphs of graphs, we can make life harder and do tournaments. What a tournament is, you take a complete graph and you direct its edges somehow. Right? And then I can, instead of induced subgraphs, I just do subgraph. A little tournament is a subgraph of a big tournament. And you can do all the same things. So fix a little tournament, which big tournaments don't contain it. And it turns out that's almost exactly like the induced subgraph properties for undirected graphs. It's there's a sort of, it's very close, it's very similar. In particular, there's a version of the Edersheimel conjecture for tournaments, and it's equivalent. It's equivalent to the Edersheimel conjecture for graphs. It says, so the Edersheimel conjecture for tournaments says for every tournament H, there exists a constant C of H, strictly positive, such that in every tournament G not containing H, so every H free tournament G. Well, before we used to say there's a big clique or big stable set. What is the analog of that for tournament? It turns out that a nice analog is to say a big transitive set. Transitive set is a subgraph making which doesn't contain any cyclic triangle. So a subgraph that can be ordered so that all the edges go from left to right. And that's Alan Park-Solomoshi proves that that's equivalent to the Edersheimel conjecture for graphs. But this has been proved in many more special cases. For graphs, I told you the complete list. If I wanted to tell you all the tournaments that have been proved to have the Edersheimel property, it's a much bigger list. So, and Maria's going to talk about that, I imagine, because it's her student that made the list much bigger. So.
Can you say again about the transitive set?
So a transitive set means a set of a definition. So it's just a set of vertices so that you can order so all edges go from left to right. So no cyclic triangles.
You said about the problem is equivalent to
the conjecture is equivalent, yes. Okay. Yeah. So one is true for all tournaments if and only if the other is true for all graphs. But the tournament one has been proved for many more special tournaments. Anyway, so that's Maria's lecture on tomorrow, I guess, right? On the Edersheimel. Let me change topic a bit. So we would like to understand what you can say about ideals that don't contain all graphs. Are they significantly different from all ideals? But we don't know how to do it. So let me change topic. Let me talk about chromatic number. Chi of G. Well, okay, if I have an ideal of graphs, there might be a bound on the chromatic number, or there might not be. You might contain graphs whose chromatic number is arbitrarily large, or there might be some constant bound. So, which ideals have unbounded chromatic number? If you have an ideal of unbounded, so for instance, let's exclude some graphs. Let's say we look at the ideals not containing these graphs, and we want to know, is still the chromatic number unbounded, or is the chromatic number bounded? So let's fix one graph. Let's take H. When is it true, for which H is it true that all H-free graphs have bounded chi? Well, so what's the answer? This one you can do. Here's a graph, and I hope that all graphs that don't contain it have chromatic number at most 10. So that tells me something about H. What? What did you say? What did you say? I mean, I hope that, what's an example of a graph? What's the most obvious graph that's got big chromatic number? Big clique. So if I hope that every graph that doesn't contain H has small chromatic number, then big cliques have to contain H, which means H has to be a clique. On the other hand, Erdős proved there are graphs with huge girth and huge chromatic number. And I think 1949, there are graphs G with chromatic number at least K and no cycle of length less than K. By the way, that's girth. Girth means is the length of the shortest cycle. So, if here's a graph and all the graphs that don't contain it have bounded chi, then Erdős's graphs have to contain it, because they have big chi. Now how can one of Erdős's graphs contain this graph? Because Erdős's graphs don't have any short cycles. So my graph must not have any short cycles. So the only hope for, if H is going to have this property, is that H has no cycles. Well, so now it's a clique and it's got no cycles. It's very, very small. It's there's three such graphs, right? There's this one, and that one, and that one. It's, and that's the complete list. Right? So not a very interesting question after all. I mean, it looked like it might have been fun, but actually it's not. It's not interesting. The reason we thought about that was it actually came out of this question for tournaments, the Erdős-Heinel conjecture for tournaments. Because for some tournaments, C of H is 1. And that, you can prove that that means, so for instance, for some tournaments they have the property of the, for some tournaments H, you can prove that every tournament not containing H has bounded chromatic number. What's the chromatic number of a tournament? It means you can partition it into a bounded number of transitive sets. You can partition the vertex set into a bounded number of transitive sets. And there were quite interesting big tournaments that have that property, that the graphs not containing H, the tournaments not containing H, have bounded chromatic number. And you know, we got a big, hard, nice, quite pretty theorem, quite interesting theorem, giving the answer, listing all such graphs explicitly. And it would have been nice to do that again for graphs. You know, it was pretty for tournaments. What about an analog for graphs? So that's why we thought about this, but it's not interesting. For graphs, it's not interesting. Too bad. So here's a way you can make it interesting again. Let's, instead of excluding one graph, let's exclude a list of graphs. So let's take a list. So when is it true that every graph containing none of this list has bounded chi? Well, what can we say about the list? Let's do what we did before. Again, somebody in the list has to be a clique, because big complete graphs have big chi, so they have to contain somebody in the list. So some hi must be a clique. What about Erdős' construction? Those, you know, graphs of big girth and big chi. They've got to contain somebody in the list. Take a graph of huge girth and huge chi. It must contain somebody in the list. So I didn't tell you whether this list is finite or not. I put dots here. There's two cases depending whether it's finite or not finite. Let's say it's finite to start with. So, right, in general, for all k, there exists hi with girth at least k. Because take one of Erdős' graphs, which with no cycle of length at least k, it's still got to contain somebody in the list, so that somebody in the list can't have any short cycles. Now, if the list is finite, how can this be true? I mean, you could be a forest. Then you don't have any cycles. You have girth, anything I want. So some hi is a forest. So there, one of the hi's has to be a clique, and one of them has to be a forest. Maybe that's enough. That's a conjecture. It's not our conjecture, it's the Jaffash-Sumner conjecture. That if H1 is a clique and H2 is a forest, then there exists N such that every graph containing neither one of them has chromatic number every graph G at most N. So if you go for excluding two graphs instead of just excluding one graph, suddenly it becomes a nice question. This is open. I mean, it's a conjecture, and it was, I wrote down the dates, quite a long time ago. Jaffash conjectured it in 75 and Sumner in 81. They're just independent conjectures, but it's been open a long time. It's still open. You might as well say it's a tree. If it's true for trees, then it's true for forests, so we might as well assume that H2 is a tree. Well, all right, so I'm interested in what you have to exclude to get bounded chromatic number. And we've seen that you have to exclude a clique. So really, let's not exclude a clique, but let's exclude some other things and look at the chromatic number you get and the clique number you get. So let's reformulate the question a little bit, and I want to look at how chromatic number depends on clique number. So let's take an ideal. Then you can look at, for the graphs in the ideal, you can look at their chromatic number and you can look at their clique number. And there's three different things that can happen. It might be that there are graphs in F with chromatic number, there are graphs, let's say G in F, with omega fixed. Let me say it another way. There are so the nicest thing that could happen is that, chromatic number is always at least clique number. The nicest thing you could hope is that the chromatic number equals clique number for all graphs in G. So that's one possibility. Second possibility is that's not true, but at least you can control chromatic number. There is a function f such that for all graphs in the ideal, the chromatic number is at most f of the clique number. And the third thing that might happen is not that either. There's no such function f. So in other words, there are graphs in the class with clique number fixed, with chromatic number getting larger and larger. Now, so three different kinds of behavior. This is a special case of that, but it's a nice function f. And this is a especially interesting case of that, so that's why I'm listing it separately. But these are perfect graphs. Maria's going to talk about that this afternoon. But suppose I want to know what do I have to exclude so that chromatic number equals clique number. What are graphs where chromatic number is not equal to clique number? There's odd holes. Because if it had an odd hole, that's got clique number 3 and chromatic number 3 and clique number 2. And it can't contain the complement. It contains no odd antiholes. What's an antihole? It's you take an odd hole and take its complement. So these will be non-edges, and all the other pairs will be edges. Right. And so if I want to exclude things to get this perfect property, the chromatic number equals clique number, I have to exclude odd cycles of length at least 5, and I have to exclude their complement. And the conjecture was, Beer's perfect graph conjecture, is that was enough. And that's a theorem Maria's going to talk about it this afternoon. That's the strong perfect graph theorem. So that's sort of understood. Remember when I was giving you descriptions of ways of describing ideals? You can define ideals by excluding something, or by constructing them, or by properties. Well, this is a description by properties, and it's equivalent to excluding something. We still don't have a construction for them. We still don't know how to describe that ideal of graphs by a construction. That's just open still. I mean, there's no reason why it shouldn't be answerable. It's just that we haven't answered it yet. Anyway, but I won't talk about that anymore. I want to talk about this. When you get a function, what do I have to exclude to get a function? Well, we kind of thought about that already. I mean, I was excluding a list of graphs, and one of them was a clique, and I wanted to know when do I get bounded chromatic number. And we saw that you had to exclude graphs of arbitrarily large girth. So if you only excluded finitely many graphs, one had to be a forest. But you could exclude infinitely many graphs. I mean, here, for instance, we're excluding infinitely many graphs. We exclude all odd cycles and all complements of odd cycles. And you have to if you want to get chromatic number equals clique number. So what if we exclude, so Jarfash asked, what if you just exclude odd cycles? That if G has no odd hole, so there exists a function f such that if G has no odd hole, then the chromatic number of G is at most f of the clique number of G. So in other words, if you just exclude odd holes, you get a bound on the chromatic number. If you exclude odd holes and odd antiholes, then chromatic number equals clique number. But if you just exclude odd holes, then at least you get a bound on the chromatic number in terms of clique number. So this was a conjecture. It's now a theorem. It's a theorem of Alex Scott and me that we proved last summer. And in the second lecture, I want to talk about the proof of that. But Jarfash actually made a whole lot of conjectures. I mean, so for instance, Jarfash conjectured that if G has no hole of length at least k, then chromatic number is at most f of clique number. You know, there exists a function f such that There exists a function f such that for every graph, so again, for all k, there exists a function f such that if G has no hole of length at least k, then chromatic number is at most f of clique number. That's still open. He also conjectured that if G has no odd hole of length at least k, then same conclusion. So different hypothesis. I mean, this is stronger than that and stronger than that. And it would be nice to prove that one. Just exclude long odd holes. But that's still open. But is there any particular reason why we're excluding odd holes? What if you exclude even holes? What if you exclude holes of length 0 mod 3? I mean, what's so special about odd holes? I mean, one reason for doing odd holes is because of the perfect graph theorem. It sort of generalizes, strengthens the perfect graph theorem a bit. But it may not be the right thing to do. There's a theorem of okay, I wrote it down. Of Bonamy, Charbet, and Thomason. Thomasay. That if G has no induced cycle of length 0 mod 3, then chromatic number, well, I don't want to say bounded by a function of clique number again, because you can't have any cliques, you don't have any triangles. You don't have any holes of length 0 mod 3. So, but what they can prove is the chromatic number is at most a constant. They give the constant, but I forget what it is. It's some big number. They conjecture 4, but they proved like 10 to the 10 or something. I don't know what it was. But that's a theorem. That's just recent. That's 2014. So it's not really clear. If you're just going to exclude cycles, you have to exclude infinitely many cycle lengths. But, I mean, there's no particular reason why you have to exclude something mod 2. I mean, what if I exclude cycles of length 0 mod 5? Would it work? I don't know, maybe. I mean, what do you have to exclude? You have to exclude infinitely many different cycle lengths. And it turns out, well, more or less anything might work. There are not many counterexamples. And we don't really know what the right conjecture is there. I mean, Jarfash's conjecture is apparently much too strong. You could exclude something much weaker than Jarfash, and as far as we know, it might still work. Anyway, I'm going to talk about that some more on tomorrow. I'll talk about the proof of the odd holes theorem, and I might also talk a bit about a different result. Anyway, for today, let me stop there. Thanks very much.